Here I'm going to define holomorphic modular forms. So function f from the upper half plane of the complex numbers is a holomorphic modular form, and then we have some adjectives of weight k, and we're going to see that k, at least for this definition, is going to be a positive integer of weight k, level n, and character chi, which is necessarily a character mod n, if and only if the following things hold. So f is going to be holomorphic on the upper half plane. All right. Probably could have seen that one coming. F is going to be not quite gamma invariant, but almost gamma invariant. It's going to satisfy that f of gamma z has to be chi of gamma times cz plus d to the power k, where k is the weight here, times the original value. And this is for all gamma and the c and d. This is me writing the matrix gamma as ABCD. This is a matrix in gamma naught n. And the third condition that we're going to require is that f is holomorphic at all the cusps of gamma naught n quotienting the upper half plane. And I'll explain what this is in a bit. So these are essentially a certain kind of automorphic form, but automorphic forms, when I use that term, I'm usually referring to weight 0. So it's nice to have this distinction. So let me explain some things about these holomorphic modular forms. So recall that 1101 is an element in gamma naught n, and what this implies is that f of z is equal to f of z plus 1. And what that implies is that f of z has some Fourier expansion of the form, it's going to be a sum over integers n of some Fourier coefficient times e to the 2 pi I nz. And what can we say about these Fourier coefficients given that it must satisfy these definitions? Well, the third criterion, that it must be holomorphic at the cusps, we can think of this as, let's set q, let's define this to be e to the 2 pi I z. So we can think of f as being a function of the variable q, and here we can write it's a sum over n of an q to the n. And this is just some complex number now. We're going to say that f is holomorphic at the cusp infinity, or I infinity if you prefer, if and only if this function f of q is holomorphic as q goes to 0. So we're thinking of q now as being a function, say, on some disk centered at the origin, punctured at the origin, and has to be holomorphic as you know at the origin as well. And then to make sense of this at the other cusps, right, we can think of f of sigma sub frac a z. So here this is going to be a scaling matrix. These were defined previously. And using the same sort of reasoning as above, right, here we said that this matrix was in gamma naught n. The subgroup gamma infinity is the subgroup generated by this matrix. And we also had other subgroups. Again, here I should maybe say that you have a plus minus if you're working over SL2Z and not PSL2Z. So this is the stabilizer of the cusp infinity, and similarly you have stabilizers of all the other cusps, and if you do this change of variables, then you can write a Fourier expansion of f at those cusps as well. So here we can write, oh boy, let me write a sub n, and then I'll put in parentheses frac a, I'm sorry. And then again, we're going to have, essentially when we change variables, we're going to have a q to the n here. And we can say the same thing, that f is holomorphic at the cusp frac a if and only if this thing is holomorphic as q goes to 0. So really what we're doing here is we're saying write f in terms of some Lagrange series expansion. And this is the series expansion after making this change variables to write everything in terms of q. So these ways of writing your modular form, these are often called q expansions of your modular form. So write the Lagrange series expansion, and then if it doesn't have any poles, you are a holomorphic modular form. There's a further bit of terminology that's going to be really important to know. F is a cusp form if and only if, let me say, the constant term a sub 0 at every cusp. No one uses this notation, so I'm sorry, this is just to convey the definition. So if and only if the constant term is 0 for all cusps frac a of gamma naught n. Basically what we're saying is that your function f of z is written some n from 1 to infinity of a n e to the 2 pi I n z. And if it's a holomorphic modular form but not a cusp form, then this would start at n equals 0. Okay, so that is our holomorphic modular form and our cusp form. And the idea with this Q expansion, all this cusp stuff, when we think about Q being e to the 2 pi I nz, and then we're saying q goes to 0, that's the same as saying y, the imaginary part of z, so z now and forever always x plus iy, y is going to infinity, right, in this change of variables. So if we think about our fundamental domain, so maybe we have this piece that's like the SL2 fundamental domain, and then maybe we have some other cusp, etc., etc. What we're saying when it's a cusp form is that as we take the imaginary part to infinity, we get that our function is going to 0. So it's saying that it vanishes at the cusp if it's a cusp form.